Hello, my name is Bruce Krayenhoff, and this is the first in a series of screencasts about quantum gate computers. My interest in quantum computers was piqued by, I did an interview with a quantum computer software company, and they're pretty crazy what they can do. So, yeah, it's in some ways it's very counterintuitive how quantum computers can work. The stuff they can do is kind of mind-bending. And you get to learn how the universe works, which is really wild. More than I did in my master's in physics, I've learned like some fundamental aspects of quantum mechanics through studying quantum computers. And yeah, it's just wild what that means for how the whole universe works. It seems like there must be multiple universes being created all the time, kind of. I'll probably talk about that a bit more later. So, my goal for these screencasts is to provide supplementary learning material that I would have found useful when I was learning. So, I'll provide links to other useful material periodically, and you'll need to go through that to actually understand these screencasts, right? These screencasts will help to answer some questions that I had while I was learning the material. Or they'll ask some questions that I think are really valuable to consider. Or they'll just help you get that higher level view so you can get more intuition for how these quantum gate computers are working, as much as we can get intuition for them. And a bit of background on me. So I graduated from physics, a master's, in 2009, so I have some background. However, that's 9 years ago, right? So I was pretty rusty. I'm still pretty rusty, I'd say. So that's kind of the level that I'll be jumping in at. Cool. So for this screencast, we're just going to review the basics of spin 1/2 particles and some, operators and how they work. Spin 1/2 particles are what's actually used in quantum gate computers. So it's important to understand them, even though, we won't actually use all of the specifics covered in this screencast. We need to at least understand the basics, and I think it's good to have a decent background. All right, and so I've defined my own notation here because it's much easier to type just an F for the factor rather than this actually typing out this factor. So I'll be using that periodically throughout the screencast series. All right, let's dive in. So mainly this screencast will be about Pauli spin matrices, which are kind of the cleaned up spin operator. So let's jump into spin 1/2 particles. They have two states. They can be spin up or spin down. Now notice I'm talking about two spin Z states. They also have spin X states, and they also have spin Y states, right? But if we're measuring spin Z, they've got two possible states that you can measure. Now why they call them spin 1/2, I'm not totally clear. Why isn't it spin plus or minus 1? I'm sure there's a good reason for this, but I don't know. And now the crazy thing about quantum mechanics is things can be a mixture of two things. So you can have a particle that's, 1/2 spin up and 1/2 spin down, basically. Or it could be 3/4 spin up and 1/4 spin down. And then when you measure it, you're actually going to find either spin up or spin down, according to those probabilities, basically. But before you measure it, it acts like it's in both those states, which is part of what allows quantum computers to do all the things they can do. So I was talking about spin Z states, but everything I said is the same for spin X and spin Y states. Now these are the Pauli spin matrices. The spin X, spin Y, spin Z. We're going to be mostly working with the spin Z matrix. Now the Pauli spin matrices are closely related to how we actually measure the spin. Since the spins are plus or minus 1/2, the eigenvalues here are always plus or minus 1. Basically, you just need to multiply the Pauli spin matrices by 1/2, and you've got the operator you actually need to measure a spin 1/2 particle. All right. So why are we representing quantum spin operators for spins in 3D as 2x2 matrices? Right? Well, it's because we either measure spin up or spin down, right? And for Pauli spin matrices, we either want to have an eigenvalue of +1, which is like your spin up, or -1, which is like your spin down, right? Cool. Yeah, so 2x2 matrices, they'll generally have your 2 eigenvalues, right? Each of these has exactly 2 eigenvalues, plus or minus 1. And if we pick the right ones here, we get the desired commutation relations, which are used, they're quite important in quantum mechanics. They have to do with how you can measure stuff simultaneously or not. So I don't fully understand this, but that's some understanding for why it's 2x2. So you get the 2 eigenvalues, the spin up or spin down, in each of the directions. So what are some properties they have? Well, if you square any of these, you get the identity matrix. So maybe pause the video, do that in your head, just multiply this matrix by itself. Same with that. You'll notice you get the identity for all of them. They are all Hermitian. So recall the Hermitian conjugate, where you do a transpose, and you do a complex conjugate. So for example, you do a transpose, so the -i goes here, the I goes here, but then you do a complex conjugate, so the -i that's now here becomes a positive I again, and the positive I that's here becomes a -i, right? So when you do the Hermitian conjugate of this, you end up getting the same matrix. Same with this and same with this. Along with i's, these are just other interesting properties to have. They form a basis over real coefficients of Hermitian 2x2 matrices. So we're getting a kind of vector space here. Just an interesting property. They each have 2 eigenvalues, and so let's look at. So these are the Z eigenstates, 1, 0, and 0, 1. You can see if you multiply by this matrix, if you multiply this by this matrix, you'll just get this back. If you multiply this by this matrix, it'll end up being multiplied by the -1, so you get negative this back. So this has your eigenvalue of +1, this has an eigenvalue of -1. Similarly, let's take this and we multiply it by the sigma x matrix. Well, this just switches these two, but they're the same, so we get the same thing back. So this has an eigenvalue of +1 for our x Pauli spin matrix, and this will have an eigenvalue of -1, because since we got -1 and +1, when we switch them with this matrix, we get +1 -1, which is the negative of this. So, and similarly for y. And how do these Pauli spin matrices here actually relate to the spin? Well, basically by a factor of 1/2. If you take this, multiply it by 1/2, you've got the spin matrix, right? So this is just kind of these are cleaned up versions of the spin matrices, right? To get the expected spin, you want to do the average over all the eigenstates, and so that actually looks like this expected value, here's the 1/2 because they're spin 1/2 particles. That's the 1/2 factor in front. And here's our Pauli spin matrix. And if you break it down into eigenvalues, this is just summing over all the eigenvalues of the spin that you get if it's that eigenvalue. So if you could repeat an experiment a bunch of times, put something in a certain quantum state, measure it, and repeat it a whole bunch of time, you would actually get this expected value. I'm not going into details here. Hopefully you've got like this background in linear algebra and eigenvalues, eigenstates to understand this. Here's a shorthand notation for this. All right. So we've gone over, we've kind of gone over the most important stuff already. I'm going to be going into some more stuff that I find interesting. They help me understand quantum mechanics in some ways better than I did way back when. Help me fill in some gaps, I should say. All right. So I guess it's important that you cannot measure spins in different directions at the same time. Okay, so you can't measure the spin in the x direction, the y direction, or the z direction. You can't measure any of those two at the same time. And this relates to commutators. So first of all, let's look what happens when we multiply two of these matrices together. Let's hide that. So, okay, we multiply sigma x, sigma y, we get I sigma z. You can just verify that. Basically, we're going to, this will multiply with that, which will give us an I up here. And then this row multiplies that, so we get 1 times minus 1, which we end up down here. So we get I and minus I here, which is just this multiplied by I, right? So sigma x, sigma y gives you that. Similarly, you can multiply sigma y times sigma z, and you will get this. Sigma y times sigma x. So this is the same two, but in the opposite order, and you get a negative. So the commutator is just this is notation for the commutator. The commutator of this just means literally. Well, that's not working. Let's figure out how to do that. All right. So the commutator, what that, the definition of that is we just take the first times the second operator minus the second times the first, and we see what the difference is. In this case, it's this. And the important thing here is that this is not 0, which means they don't commute. If they did commute, then, hold on. If they did commute, then we could just, measuring y then x would be the same as measuring x first and then y, because, the difference is 0. But they don't commute, which means that x and y spins cannot be measured at once. All right? I'll go into this in a bit more detail later. Similarly, these are equal to this, so we can't measure spins y and z at the same time, and so on. More generally, if we take two of these, we get I times this thing here. And what this thing is say if I is x and j is y, so we've got sigma x, sigma y, just like that, then this thing is going to be 0 unless k is the other one. So I was x, j was y, so k had better be z, right? And so then if k is z, then this is 1. And so then we'll multiply it by that. And then there's Einstein notation here, which means we see k occurring twice. We actually sum over all values of k. But remember, if k is also x, which is the same as I, then it's going to be 0, right? If k is y, which is the same as the value of j, then it's going to be 0. It's only when k is different, it's only when all three of these are different that we get something non-zero here. So similarly, say this I was z, and say that j was also z. Well, then I and j are the same here, so this epsilon thing is 0, right? So this is, hopefully you've seen Einstein notation, otherwise I'm throwing a lot at you at once. But this is a kind of a succinct way to capture all of these formulas as a single formula. And then we can do the commutator. Oh, right. So the other thing, these have an order. So if it's epsilon x, y, z, this will be plus 1. If it's epsilon y, x, z, so I've switched the x and the y, this would now be negative 1, right? So this formula also captures when we switch the order, we get a negative. Cool. And so in general, this is the general formula. This commutator is equal to this. So the spins in no two, I should say, perpendicular directions here. Probably, as long as the directions aren't parallel, they cannot be measured at once. All right, but you can measure the total spin simultaneously to a directional spin. So to get the total spin squared, right? We do Pythagoras, right? So we just need to get the x, y, z. This ends up being 3i because each of these squared gives you I, so it ends up being 3i. So the total spin is always root 3, and I commutes with anything, right? So we can measure the total spin along with any single directional spin simultaneously. All right, so I want to go into a bit more detail about, we've got these commutators. They don't commute, so I say they cannot be measured at once. I want to go into a bit more detail in this, and we'll be talking about like how measurement actually alters the state of something, at least as far as we can observe with our own state, which is the wild thing. So let's close up those. Okay, so in quantum mechanics, why can't you measure things at the same time if their operators don't commute? So I found this great, some great answers posted here. I still don't understand this like 100% in the depth I would like, but hopefully this helps you understand how this works and how measurement works in quantum mechanics a bit better, which will be useful for quantum computing. So when you make a measurement, you get back one of the eigenstates. So let's say we've got something that's in the state 1, 1. Okay? And so if we measure it with x, this will just give us back exactly the same vector. So this is already an eigenstate of the sigma x vector. And so what our measurement will give us is +1, because this is the +1 eigenstate. Cool? So originally we have it in the spin-up eigenstate of sigma z, and so our measurements always give us 1 if we measure sigma x. If instead, what if we measure the z spin of this first, and then later we're going to measure the x spin? Okay? So first of all, when we measure the z spin, it actually puts it in one of the z eigenstates. Let's close that. Maybe I'll... Yeah. All right. So, okay. So for the z eigenstates, so I want to represent this. Okay, so remember f is our like 1 over square root of root 2, right? So this is actually equal to f times f times 1, 0, and f times 0, 1. All right. So remember, this is the up eigenstate, and this is the down eigenstate. So to get the so now we've got it expressed in terms of the eigenstates of z. So the probabilities are the number in front squared, right? So we just take this f, which is 1 over square root 2, we square it, which gives us 1/2, and that's how we get this probability. The probability of it being I guess, spin up. And then we take this squared, and that gives us the probability of it being spin down. Okay, so there's a 50% chance that we measure it as being spin up, and then a 50% chance that we measure it being spin down. Cool. So this is the quantum state before measurement. And then we're going to have the quantum state after measurement. And so we have these probabilities. So the quantum state after measurement is going to actually just be whoa. So 50% of the time we measure this state, and then after we measure this state, now this is the quantum state, right? The quantum state is now spin up. We've altered the quantum state by measuring it. Or another way to interpret this is that we have actually correlated, all the quantum stuff that makes up our brain, because ultimately we're made up of tiny particles that are quantum, right? That we are all correlated with the up quantum state. And in an alternate universe, another one of us is correlated with the down quantum state, right? That's the wild thing. Seems like the most logical interpretation of how quantum mechanics works. All right. And so now after we've done the measurement, we're either in this state or in this state, right? We're no longer in this mixed state in terms of z's. So if we then go and we measure x now with this, if we're in this state with probability 1/2, then well, we can take that and we can split it up and represent it as the x eigenstates. So this would be the +1 eigenstate, and this is the -1 eigenstate. And it's actually 1/2. That's not correct. That should be an F there. No, that was correct. Yeah, because these vectors are not normalized here. So I get 1/4 when I square that, and that squared gives me 2. So yeah, it all works actually. But the important thing here is now we're equally likely to measure spin up or spin down in the x direction. So even though originally we were in the x direction, measuring the z direction totally messed that up. And now in terms of the x direction, it's a 50-50. Same, and it's actually the same if we measured spin up or spin down in terms of z. Either way, now we're 50-50 chance of being each in the x direction. Cool. So basically, from a practical purpose, measuring destroys the quantum state, and you get a measurement that's based on the probabilities, right? You measure either one or the other. Cool. Okay, so that's how measurement alters the quantum state. So then when you make later measurements, it's different, right? So you can see here how like we can't just measure z and then when we measure x, like our results are altered, right? It was spin up, but after we measure x, now we've 50-50 chance of getting spin up or down in the x direction. Yeah. Cool. So I wanted to go over a bit more theory about like when does this happen and how does this relate to operators commuting. All right. Okay, yeah, we just went over this. Now, if we had two operators, if they have the same eigenvalues, then let's say they're the same eigenvalue. We can use those eigenvalues as our basis vectors, and then we could see that if we measure sigma z first, then sigma x, our result would be the same as if we just measured sigma x. So let's say that, let's go up here. Say we measure spin up. So there's 50-50 chance of each of these. Say we measure spin up. And now if we applied the same operator, if we apply sigma z again, since it's now collapsed into the state, we would measure spin up again. And so our probability of measuring spin up would be the 1/2 probability that it collapsed to this state in the first place, and then 100% probability that it stays in that state. So overall it would stay a 1/2 chance that we'd measure this the second time, because sigma z commutes with itself, right? Or it has the same eigenstates as itself. We could have an operator to measure negative sigma z, the spin in the opposite direction, and it still has the same eigenvectors, and so we'd have the same result. So hopefully you can figure this out yourself. I haven't gone into too much detail. Also, if they've got the same eigenvectors, they would definitely commute. You can just look what happens to each eigenvector. Okay, we multiply by the first eigenvector, and then by the second, or first eigenvalue, then by the second eigenvalue for that component of the vector. And if we multiplied by the operators in the opposite order, we'd multiply by the eigenvalues in the opposite order. And the eigenvalues are just numbers, so they commute, so the operators commute, because we can just work in the basis of these eigenvectors. So I want to look now in more depth at what happens when they don't commute. So I'm guessing that when operators commute, they pretty much always have the same eigenvectors. It might always be that way, or pretty much always. Think the stars have to align in order for this not to happen. I'm not sure. But we'll go through an example which shows how if they commute, then they have to have the same, if they can be measured at the same time, then they have to have the same eigenvectors, which means that they would commute. So suppose we're in, alright, so this is the z eigenstates. If I is equal to 1, it's the first eigenstate. If I is equal to 2, it's the second eigenstate. There we go. Cool. And so we could represent this z eigenstate in terms of x eigenstates, right? Okay, so there's a way to switch between them. So let's look at what happens if we don't measure sigma z first, right? We just measure we're going to use I guess sigma x to measure first here, and this can be plus or minus 1, right? So we're just going to look at one of these probabilities, the probability that we have the eigenstate corresponding to the -1 spin. I think I might need to make this table a bit smaller. All right, so this is our initial eigenstate. So we've got, alpha squared is the probability that we're in the z direction. This alpha also has a phase, i.e. it could be plus or minus 1, or it could be imaginary. Beta squared would be the probability that it's, I guess, downspin in the z direction. Cool. So we can take this, we can use this formula, we can express it in terms of the x eigenvectors. And so then the chance that we measure a -1 is I guess I'm assuming that this is the negative spin. So chances of measuring this would just be, well, we need the modulus of this squared. So like absolute value squared. It's a modulus. I mean, it's complex numbers, right? So modulus squared, we can expand that into this. And this part, we can say that's just the real part of that. Okay? Cool. So this is if we don't measure sigma z first. We just go ahead and we measure sigma x right away. Now if we do measure sigma z first, then it's going to collapse, right? It's either going to collapse into this state or this state. So we get, we either get this state or this state with these probabilities. So if it collapsed to this state, then the quantum state in terms of x eigenvectors is this, and so the chance that we then measure a downspin is going to be this. Now the chance that we collapse to this state was that, and so overall the chance that we collapse to this state and then measure a downspin is going to be this, right? Similarly, the chance that we collapse to the up z state and then we measure a down x state is going to be that times that, which gives us this term. And if you notice, these terms are the same as these terms. But when we left this combined state, we also got this additional term, right? So it seems like, measuring it here has affected the probability that we measure the down state because we lost this term. So measuring z has changed the probability that we measure the down state in the x direction. Down spin in the x direction. What the heck? Looks like I've deleted some stuff. Anyways, okay, so for these to be equal, this has to be 0. How did I do that? Man. Huh. Anyways. So yeah, so this equals 0 for all, no matter what our initial quantum state is, we want the measurement to be the same, right? So that should be for all alpha and beta. If measuring z doesn't ever change the x we measure, right? Or the probabilities that we measure each x state. And so it's the real part of this has to equal 0, but I mean, we can change this by factors of, e to the I theta to rotate it around, so any part can become the real part. So basically, the only way to do this is to make the whole thing 0. So this means that that has to equal 0. For all alpha beta. Interesting. And the only way for that to happen is really that A1 equals 0 or A2 equals 0. Cool? So one of them has to equal 0, and if we considered the probabilities of measuring spin up, we would get that the other one has to be 0. So either way, one of the A's has to be 0, and we'd get that one of the B's has to be 0, I think. Yeah. And what this is saying is if one of the A's is 0, for that Z spin, it corresponds exactly to the other X spin, because one of the A's is 0, right? And the other B will be 0. And so what this is giving us ultimately is that the Z eigenstates are exactly the X eigenstates. Cool? So that's the result. They have the same eigenstate if measuring Z doesn't change the X we measure. And we know if they have the same eigenstates, then their operators will commute, right? And I'm guessing it's pretty much always the other way around. But it's like I don't have enough tools or background to definitively pin this down myself. I'm sure there's like a higher level, more general understanding that some people have of this. Cool. So lastly, I want to go and talk about raising and lowering operators. I haven't seen this in quantum computing at all. This is primarily for my own interest, so feel free to skip to the next video if you're just interested in quantum computing. So this is from Wikipedia. Apparently, raising and lowering operators, these are where you have a certain operator with eigenstates, and then you have another operator that maps between the eigenstates of the first operator, right? And so we're going to look at an example of a raising operator. So first of all, recall the commutator of this is equal to this, and the commutator of this will be negative that, because remember, these are kind of in the right order. It goes x, y, z, so that's why this is positive. But it should go y then z. These are in the wrong order, which is why we get a negative in the commutator. Then we create, this is the raising operator. We're going to see why this is the raising operator. So it's this. So if we do z commutated with that, well, we're kind of going to get both of these. We're going to get this term, and then we're going to get this term, except with an extra I, which will make this 2 sigma x again. And so therefore the commutator of this will actually just give us back this, except it'll be 2 sigma x and it'll be 2 I sigma y. So it'll be the same thing with a factor of 2. Okay, that's interesting. Now this property is what will make it a raising operator. So if we look at what happens here, so if we apply sigma z, so here we're applying the raising operator first, and then we're applying sigma z to what we get. So this would be the same to the commutator, which is this minus the other way around, plus the other way around, which is what we have here. So that's equal to this. This commutator we know is just 2 of those. Okay. And then we know if we apply this, so this, we could factor it out to that. If we apply this to an eigenstate of sigma z, so here S is an eigenstate of sigma z, then, okay, so this is equal to, we just derived that is equal to that. And then we know sigma z will just give us back S is an eigenvector, is an eigenstate of it, so we're just going to get the spin of that eigenstate times the state back, right? And then now these are just numbers, right? So we can just bring this in, and so we get that. So ultimately, sigma z applied to this gave us this number times the same thing back, which means that sigma plus s is also an eigenstate of sigma z. And the eigenvalue is the number that you got multiplied out front, which is 2 plus sz. So it's it's the next eigenstate, the eigenstate with an eigenvalue 2 bigger. In other words, if we start with the downspin, which has an eigenvalue of -1, after we apply the raising operator, now the eigenvalue will go from -1 plus 2, the eigenvalue will be +1, right? So we can start with a -1 eigenstate and raise it and get out the positive eigenstate. So that's a cool trick. Get one eigenstate, now we can get other ones from that. And we can also use this to solve for some other stuff. That goes back to my calculus course. I'm not going to get into the details. We can actually solve for the states using this. And similarly, we could create a lowering operator. But yeah, that's about all I wanted to go over. So here in Wikipedia, they have more general example. So when you've got angular momentum, or you've got, a spin 1 or spin 1.5, other spin states, you can create raising and lowering operators between those states as well. And for that, I recommend you read a bit of Wikipedia. All right, thank you very much for watching. In the next video, we will jump into the quantum gate computers. Bye-bye.